Welcome to this lecture in NPTEL course. We are continuing the discussion on paraboloid reflector system. We have seen the aperture field distribution from the feed's radiation pattern. Now, we will see the directivity of this whole system, that means aperture directivity. So, we know actually in few lectures back we have proved by Fourier transform method that for a uniform constant phase aperture field with linear polarization, the radiated field is given by the expression ER j k naught e to the power minus j k naught r by 2 pi r a theta f x cos phi plus f y sin phi plus a phi cos theta f y cos phi minus f x sin phi. This we have already proved. Now, our aperture is circular with radius a in z is equal to 0 plane. So, we can write our aperture field is E naught a y, a linearly polarized uniform electric field. We are assuming it. Now, we have seen that it has got problems, but first let us see the directivity, that means what maximum we can achieve if we can create this uniform field. Let us arbitrarily I have taken y polarized field in any single polarization. So, this is valid for x square plus y square less than equal to a square. This is a circular disc, and 0 otherwise. So, with this EA, what will be my Fourier transform FT? FT will be E naught, E naught, that AY, then on the aperture e to the power. So, this is 1 into e to the power j k x x e to the power j k y y dx dy. Now, to evaluate this integral evaluation is not so easy. So, I will help you. So, since this is a circular disc, we introduce the polar coordinates, but since it is the aperture is here source, we say the polar coordinate is rho. Instead of phi, I call it phi dashed. I should have called it rho dashed also, but it won't get confused because the other feeds thing is theta. So, since it does not have any theta, so there is no confusion, but since there is also phi, so the observation field phi and source field phi, that is why I am saying phi dash. Now, what is my rho? Rho is nothing but root over x square plus y square. So, x is equal to rho cos phi dashed, y is rho sin phi dashed, and also we know k x is k naught sin theta cos phi and k y is k naught sin theta sin phi. So, I can put it on that FT expression. So, it becomes E naught A y, then 0 to a 0 to 2 pi e to the power j k naught rho sin theta cos phi minus phi dash rho d phi dashed t rho. Okay. Now, this thing e to the power j something cos that can be, that has a series expansion. Anyone knows that series expansion is in terms of Bessel functions. So, we can write, if I have E j some constant into cos phi minus phi dash, the Bessel expansion is j naught, that w you can say, or omega, whatever. This is a constant, that means j into these. So, j naught omega minus 2 j 2 omega cos 2 phi minus phi dash minus j 4 omega cos 4 phi minus phi dash etc. etc. plus 2 j 1 omega cos phi minus phi dash minus j 3 omega cos 3 phi minus phi dash plus etc. So, big, but so what is the, if I write j n omega for various subscripts. So, this is the Bessel function which comes in all engineering science problems. So, Bessel function, this is j means it is the first kind and n means of order n. Okay. Now, the, if I put it here, fortunately the integration of this cos 2 pi minus phi dash, where phi dash is varying from 0 to 2 pi cos 4. So, everything from 0 to 2 pi integration, that becomes 0. Only the thing is who does not become 0 is j 0 omega. So, f t comes out as E naught a y 0 to a 2 pi j naught. You will see that k naught rho sin theta rho d rho. So, it is an integration of Bessel function of 0 order. So, there is another formula which will help you. So, with this formula you can find out that this will become 2 pi E naught a y 0 to k 0 a sin theta j naught k naught rho sin theta k naught rho sin theta by k naught sin theta d of k naught sin theta, sorry, k naught sin theta rho by k naught sin theta. So, if you do that, it finally becomes 2 pi a square E naught a y j 1 k naught a sin theta by k naught a sin theta. Now, on the z axis, theta is 0. So, k naught sin theta fully 0. So, this j naught 0 by 0, this term will give you j naught 0 by 0. Now, so that is L'Hospital rule. So, you will have to differentiate this and then put the limit. So, this part gives you half. So, it becomes pi a square E naught a y. On the z axis, the E plane pattern is theta is equal to 0, pi is equal to pi by 2. So, we get f y will be pi a square E naught and f x is equal to 0. So, we have f y f x I have got. So, we can say that E radiated field, that will be j k naught to the power minus j k naught r by 2 pi r. F y you can put, or I will write f y a theta. So, that will be j k naught E naught by 2 pi r e to the power minus j k naught r pi a square a theta. So, this will be the far field. Now, the power density per unit solid angular radiation intensity in this direction will be r square half y naught E theta square. So, I will say power radiation intensity, I will say radiation intensity along z axis, that will be this. So, if you do, it will become 1 by 8 k naught square E naught square y naught a to the power 4. Another thing we need, the total radiated power PR. So, for that will be over the aperture, the pointing vector into dA. Now, pointing vector over aperture is what? Pointing vector over aperture, that actually here we can say that though aperture is not very far away, but we are having the already a parallel beams, and it has been, it can be proved that there the magnetic field is also like the far field, that means that n cross that thing. So, we can almost take it that it will be half y naught E square, E naught square. So, just like far field it becomes there. So, if this is there, the total radiated power PR will be half y naught E naught square, then the area 0 to 2 pi, 0 to a, rho d rho d phi. If you do, it becomes half pi square y naught E0 square. So, now you are in a position to do directivity 4 pi into that radiation intensity 1 by 8 k naught square E naught square y naught a to the power 4 by total radiated power half pi a square y naught E naught square. This gives you, or I will write it like this, directivity is 4 pi by lambda naught square such a simple formula, such a useful formula. Now, what is it? Pi a square means what? The aperture physical area. So, aperture physical area is getting multiplied by 4 pi by lambda naught square. So, if you have a dish of 1 meter radius, then pi, so 4 pi square gives you 40 roughly, and if you are at 10 gigahertz, 3 centimeter means 0.03 into 0.03. So, 0.009. So, I can say 0.01. So, that means 4000 is the directivity. 1 meter radius can give you directivity of 4000. Quite remarkable. But obviously, we cannot, but this is directivity, that means there are no losses. Now, actually there will be losses, etc. So, the maximum directivity obtainable from an aperture antenna with a constant phase uniform field is physical area multiplied by 4 pi by lambda naught square. Very simple formula, easy to remember. But what will be the gain of the paraboloid antenna, reflector antenna system? That will be G is equal to 4 pi by lambda naught square into pi a square into efficiencies. Now, these efficiencies, the first one, actually we will see a long list of efficiencies at the end. Initially I am writing eta, that eta to start with I make that there is a two things, eta s, eta a, later others will come. So, I will say this. Now, this I will see first this, then the others. Now, this eta s, this is called spillover efficiency. Spillover efficiency. Eta a is aperture efficiency. Now, aperture efficiency I need to talk a bit, because whatever we have done, that if I have an uniform illumination, if I have a constant phase illumination, if I have a single polarization aperture field, then I get the directivity I have found. Now, aperture efficiency is violation of all these. So, aperture efficiency will comprise of illumination efficiency, because we have seen that there is a taper and it is desirable from the application point of view. So, it will be multiplied by eta I, then it will be that phase. So, uniform phase, we have we know that there will be a phase error. So, that is phase, and I think that third part is sorry, this is polarization. So, the next one non-uniform thing, let me call it taper T, we don't say eta x. So, this is due to non-uniform illumination. This is due to phase error, due to phase non-uniform phase, and then eta p, it is the cross pole, presence of non-linear thing. So, spillover efficiency, what is it? Spillover efficiency is that some radiation from the feed is not intercepted by the reflector, because reflector is finite, it has an angular aperture. So, it is not intercepting all the rays. So, power is lost there, and definitely then we are assuming total power radiated, but if that power is not reflected, so ultimately aperture is not getting that power. So, gain will definitely reduce. So, that is called spillover loss, and efficiency factor due to that is called spillover efficiency. So, what is spillover efficiency now? So, I am now talking of spillover efficiency. Eta S is power intercepted by the reflector by total power radiated by the feed. Okay. So, what is it? Power intercepted means I have G theta phi is the power radiation pattern, sin theta d theta d phi, and so phi is 0 to 2 pi and theta is from 0 to psi by 2, half of the angular aperture, because 0 to 2 pi I am giving. So, here 0 to psi by 2, this is the power intercepted by the reflector, and here 0 to 2 pi, 0 to pi, g theta phi sin theta d theta d phi, that is all. That is spillover efficiency. Okay. Now, ultimately we will see that I am not interested to find simply this spillover efficiency, or it is we will later see that jointly what happens here. Actually, the others can be separately done, but these two are, as physically I explained, that if I want to have an uniform illumination, then spillover increases. That I said earlier, that the best possible illumination was that sec to the power 4 theta by 2, but that gives lot of A. So, these two are coupled and one affects the other. So, that is why we will jointly maximize these instead of trying to do that. Now, to that end, instead of evaluating it further, what I do, I want to put here the directivity of the feed. That means, this is radiation pattern, here I want to put the directivity of the feed. So, df. Now, what is directivity of the feed? df, let me write directivity of feed df. What will be its expression? 4 pi G 0 by total radiated power by feed. Okay. So, you see that this is nothing but total radiated power by feed, this denominator. So, can I write that eta s is df, then 0 to 2 pi 0 to psi by 2 g theta phi by, actually this will come out 4 pi g 0 sin theta d theta d phi. Okay, I leave it here. Okay. Now, next I start. I will use that, as I said that since I will jointly do. So, I will take this after finding an expression for aperture efficiency eta a. So, who gives this aperture efficiency? The loss in gain due to, first I have a tapered electric field in the aperture. Then non-constant phase for aperture field, and then presence of unwanted cross polarized field. Okay. So, actually this expression is available or it can be derived, but I won't do that because that will be more mathematical in nature. So, I can write eta is eta I, this is called illumination efficiency, then non-constant phase is phase error efficiency, and cross polarized thing is eta x. So, this is illumination efficiency, this is phase error efficiency, this is cross polarized efficiency. So, I am not going, there are some long list of things. So, we assume while deriving this illumination efficiency that eta p and eta x they are 1, later we will put their values. So, under that assumption it can be derived. If anyone interested, please see in the maybe in the course page we can upload this the derivation, but finally what we need is that eta I, the illumination efficiency, that becomes an expression something like this. This is the expression that is obtained for the illumination efficiency. Now, if you do not believe this expression, I can give you a check. For uniform aperture field, we require that g theta phi should be proportional to sec 4 theta by 2. Put that in this expression g theta phi values, and eta I should turn out to be 1, then that will be a indirect way of saying this expression. So, you can do that if you put it there, you will see this will become sec square theta by 2 tan theta by 2 d theta. This whole thing will come out because g theta phi is independent of phi. So, the phi integration will give you 2 pi, and here also you can integrate. So, you will see that under that assumption that g theta phi is sec 4 theta by 2, this eta I expression becomes 4 f square by s square 10 square pi by 4. Already we have found the value of A when we derive that rho is equal to A is 2 f tan pi by 4. So, put that value of A. So, eta I becomes 1. Putting it here, it becomes 1. So, this expression is correct. So, now we will see that how to manipulate these, that we will see that this jointly, if we put these two expressions eta I and eta s, how to manipulate that, but that we will see in the next class. So, we have now found out the illumination efficiency. Found out means this is, I have given this formula, and the spillover efficiency we have derived. So, now we will see how to play with that as an engineer in the next class. Thank you.